something most peculiar happened when I was trying to record the last video, and everything cut out. Everything cut out. Cut out. Cut out. I say at the 15-minute mark, at least in terms of this particular camera. So we're back at it again. We've got a chunk of note that I attempted to record and failed, and I'm going to walk us through it quickly to sort of catch us up. So previously on chemistry, we were talking about electron sharing and how this is something called a covalent bond. And the reason we're calling it sharing is because we're thinking of an electron sort of being pulled towards another atom. And for some reason, this is an electron pair sort of takes place. It performs this action. We didn't go into that because it's weird. Yeah, it's quantum, literally. So moving quickly past that, if an element impacts another element, this is the way we're going to think about it in terms of chemical interactions, where we usually think of atoms striking other atoms. This originates to some extent back to ideal gas theory, whereby we're looking at what an ideal gas sort of theoretically looks like, what a container filled with sort of the simplest material and how we would model that, essentially. And the answer is basically we sort of take a very basic container, preferably in two-dimensional space, which is always a little simpler, and we have a bunch of point particles that we can bounce around inside of it, and that gives us a very basic way of simulating a gas. Yay! Anyway, let's get back into our dealing with some of the applications of our elements, as opposed to thinking of the individual materials. If an element impacts another element in its electronegativity, this is a really important concept related closely to polarity, is so strong that it can pull the electron right off the other atom, the following circumstance arises: ionic bonding. So here we're introducing the concept of bonding being sort of a spectrum, right? You are bonded at different levels of intensity by a particular strength of electromagnetic force. And I think that's really the sort of essence, the basic essence of bonding. There's a bunch of different electrochemical forces that arise from this bizarre interaction of electrons going around protons in a nucleus, right? And there's all of these different elements that have different configurations, different numbers of protons, different numbers of electrons, and even neutron interactions as well, though those seem to play a relatively little role in most sort of bonding scenarios, as far as we can tell, and to my knowledge. So that gives us like a whole spectrum of different forms of bonding. And this form of ionic bonding, some people find it simpler to understand. I actually find it a little weirder. The thing that I've been trying to explain here, these are supposed to be arrows, is the positive and negative charge on these ions. So these guys are ions. You know that they are ions because they have to be ions. They've got these little negative and positive signs upon them. This is 11 protons, which if you look up on a periodic table of the elements, sodium has 11 protons on it. And here we have one electron on the outside. This is represented eventually by this Na plus ion. Right now, this is actually the neutral configuration, right? The neutral configuration, which is just Na. This is also, that's the neutral configuration of potassium. So sodium chloride of chlorine. So this is the neutral configuration of chlorine, Cl. But in this particular ionic setup, what makes it an ion is the fact that this electron over here has been placed over here onto this Cl. And that means that it has an extra E negative charge, which is why we give it this negative. It has another negative charge. So I find that a little complicated to explain. I find it quite easy to understand once you get it, but the basic challenge is, of course, the fact that you're adding on something, but it's a negative charge. Some people get it immediately. They're like, piece of cake, why are you talking about this so long? Some people really struggle with it, which is why we're hanging out with it for a moment. By the same exact logic, then, we've taken away a negative, so this now has a positive charge. Yeah. Basically, Na here over here is 0, right? If we have a negative and we take away a negative, minus 1, then we get a charge of positive 1. Right, so that gives us that value there. And then the exact same sort of thing here. Here we're adding on electron, 0 minus 1 equals negative 1. Cool. All right, so that sort of catches us up roughly to where we were with ionic bonding. The result of this stealing, you'd think, okay, well, that's all good. NA's lost his electron. He can go off, do his own thing. No. Unfortunately, this plus is now like it's got this like extreme form of polarity, right? It's like intensely polar, and so does this Cl minus. In fact, it's so polar it's got its own name for it. We call it an ion. Yeah, crazy. And this negative and this positive actually is it corresponds directly to an equivalent imbalance in the electronegative force. So even though technically this proton has like stripped off an electron, in reality this has resulted in like an imbalance, like a magnetic imbalance, you can think of it as, between these two things that has to immediately cause them to like lock onto each other. If that makes sense, right? So if this is like a strong pole and this is our Na plus and this is our Cl minus, the moment one of these electrons is stripped off, it like creates this very imbalanced structure, and the only way for them to satisfy each other really easily and quickly is to like immediately jump together. So that's why, unless there's a really powerful set of intervening molecular forces, like, I don't know, hydrogen bonds, but we'll come back to that. Unless there's a really powerful set of intervening forces, these guys will just leap together and they'll actually combine to create, if you think about it, you have this sort of like really rigid setup of order and structure. They combine to create a crystalline structure, because it's very rigid, so it always has to sort of stick together in the same sorts of ways. I'm doing a pretty bad job of drawing that, but imagine this was all sort of in the same, there we go. Imagine we were all sort of dealing with things in the same sort of orientation and pattern and structure. See, what I should have done is drawn the thingy first. Right? So we've got a three-dimensional space here that's in a structure, and if I can go up a layer, something like that. Yeah, that's pretty weak, but if I go up a layer, then you can see we can keep adding to this structure, and it becomes this like three-dimensional, preferably lattice, basically. And this is the essential basic structure of salts and crystals and all that good jazz. Yeah. So let me double check in here with my note, make sure I'm not getting too carried away. Excellent. So having hinted at it just a moment ago, let's go back in. So we've talked about bonding in terms of stealing electrons. We've talked about bonding in terms of sharing electrons. Bonding is unfortunately a topic that, if we were to rearrange the great structures and sections of science, we probably wouldn't collect everything that we call bonding under the same name now. Our understanding of bonding has changed really radically since we first started mixing chemicals together and understanding that we could create new things out of old things. And that's the sort of, there's really sort of two perspectives by which we come at chemistry. And one of them is from the very familiar perspective of some guy in a lab, some mad scientist mixing chemicals together and trying to create things. And the other perspective is the perspective that I'm trying to get across, which is a much more molecular perspective, a perspective about how individual atoms are interacting. The remarkable thing about chemistry is that these two perspectives are consistent, but it takes some work to actually move from one to the other and understand how that's happening. And really the only way that we've been able to build that up knowledge-wise as people is because we've done a ton of experimentation and we've recorded it and shared it. That's why that's such an important part of the scientific method. So, last major topic here. Tiny bit of coffee. Last major topic here. The whole chemistry section, can you believe it? Numero 12. Hydrogen bonding. Hydrogen bonding. Hydrogen bonding is really cool. It's really weird. It's very special. all the sorts of good things. So in the other forms of bonding, there's competition over electrons. In the other forms of bonding, there is competition over electrons. In this form of bonding, it is the direct interaction between a mass of polar molecules that produces conditions for bonding. So this is a new and different way of thinking of bonding in terms of stealing and sharing electrons, but I've been trying to prep us for it by thinking about things in terms of polarity and electronegativity and sort of balances and imbalances in these sort of fields that are surrounding our atoms. So, the name comes from the role that hydrogen plays in hydrogen bonding, and we usually think of it as taking place in water. H2O. So here, the H's are, of course, what is important and relevant. I'm going to draw two different structures of water very quickly for you. This is one structure you're all probably very familiar with. This is a slightly different structure. How am I going to do it? I'm going to do it like this. This is how we typically try and draw atoms. These ones aren't scaled for size, which is totally a-okay. But last but not least, I'm actually going to grab another color here. I'll take that. Okay, kind of makes sense. All right. So these, I'm essentially trying to shade on these like electron clouds. Yeah, not bad. Cover up my other H bit there, but that's totally okay. And what I want you to notice is basically we've left this bond at just half and half, right? And that's not really what's going on inside this bond, but we've left it at half and half for visual purposes so that you can see that the electron cloud itself features an imbalance, right? The electron cloud itself is imbalanced, right? And this is what produces polarity. But it also explains the overall shape of the H2O molecule, right? So the overall shape of the H2O molecule is that these outer hydrogens, they're like forced more closely towards each other, and they're kind of like, it's almost like they're being pushed away from this oxygen, right? This is due to the imbalances of charge involved. And if you start thinking about the negative nature of certain parts of it, you start thinking about how magnets work, all that good stuff, then hopefully these things will start to make more sense to you. One of the simple ways to understand it, however, oh my gosh, I left two vital little pieces out of my diagram. Here we are. One of the things to understand it is in terms of these lone pairs. So these electron pairs over here, we can think of these as kind of like occupying their own sort of space, right? And because of that, they take up the other angles that we would expect if there were additional hydrogens being bonded onto this oxygen somehow, we would expect there to be a hydrogen off here and a hydrogen off here, and it to create a balanced three-dimensional molecule, right? If instead these are taken up by these like invisible seeming sort of lone pair concepts, then these guys end up in this respectable shape that makes more sense to us. We just have to account for the fact that we have this strange new thing that's running around distorting the shapes of our molecules. This is a sort of basic challenge with looking at chemistry from a molecular angle. If you are combining chemicals and just trying to mix stuff and make things, then you really don't run into the same sort of issue in the same sort of way, because you're much more focused on the result that shows up. If you're trying to understand exactly how these things work, in terms of what is occurring on a molecular level, the questions become much more complicated and much more peculiar and weird. And we'll talk more about that in physics at some point. So, last thing I want to do, this chemistry section has gotten broken up. It's taken too long, yada yada. That's all good. We've covered some really important information. And I just want to make one final summary. Chemistry. Summary. So, intro to chem. Why did we do chemistry? What have we covered in chemistry? So, it's been really important. We've talked about chemical reactions. We're going really important, useful places with some of this stuff, but we've got to cover the basics first. We've talked about chemical reactions, ions, and molecules. You started to gain, if you're totally new to this stuff, you started to gain some basic familiarity with all of these really important concepts. We started to talk about particular types of molecules, specifically carbon backbones. And this led itself to this entire sort of subclass of molecule, though there's several different names for these things. Hydrocarbons, they're also known as, and simple organics. There's lots of sort of overlapping names for these particular things because they're so common and important. So this allowed us to discuss some of the basic ones. Basic organics. We, of course, talked about ATP, which is really important. We talked about glucose for sugars. We talked about an amino acid. Which one did we cover? Glycine. And, of course, the roles of amino acids and things. And we were basically, all we were doing in this section was we were building molecules out of these sort of simple structures that we'd learned already. Okay, we can have ions, we can have different molecules. These things sort of fit together in different ways. Let's start looking at examples of them, and then we'll try and figure out just a little bit about how they work. Last but not least, we looked at some fat. Myristic acid. And we started to notice that there were chemical bonds involved. Chemical bonds everywhere. And we started to dig into the very complicated topic of what those things might be. Next up, we're going to start looking at some applications of chemistry in biology, specifically in terms of the cell and basic structures of the cell. This will be kind of a mashing together of the previous two units that we've done, and it'll take us to some even more interesting places, and hopefully get us into some more advanced material as well. So I hope you've enjoyed chemistry, and have a great day. You're the best. Believe in yourself. Bye for now.